Okay, let's look at some other types of junction diodes. One of them is known as the optoelectronic devices. So the more famous one, which is used probably everywhere, is the light-emitting diode. It's a diode which emits light. So it emits light when it is forward biased. Okay. If you buy it, you will see that it will look like a bulb with two leads. The positive lead is the longer one. The shorter one is the negative. So longer is positive for the P, and that's how you know how to connect it. The symbol for the LED is a diode symbol, right? But then you show it emitting light. That distinguishes it from just a junction diode. So how will you connect it? Well, this is how you'll connect it. You will connect a voltage source to the diode in forward bias. So this is positive. Okay, so if you do this, then you'll see that the diode will blow off because the current is going to be a very high value. So what you want to do is you want to limit the current in the circuit by using a resistor. Okay, so let's say that this is 5 volts. The typical voltage drop which you need, which drops across the diode, is the potential barrier. Remember that we talked about earlier. The potential barrier for a junction diode was 0.6, 0.7, but for a diode is about 2 volts. Okay, so the bigger potential barrier. So we want to now compute what sort of resistor we need. So it's actually not very hard. So let's assume that the current is I. Then we can see that 5. So using KVL, we have 5. This was negative. So 5 minus 2 minus IR equals 0. And so we have 3 equals RI. Now the question is, how will you choose R and I? So typically, if you look at the spec sheet, it will tell you what is the maximum current the diode can take. Let's assume it to be from spec sheet. Let's assume I is given to you, let's say 10 milliamps. Yes, it's a very small value. So we can then find the resistor just by plugging it in here. 10 times 10 raised to negative 3, which is 0.01 R. And R comes out to be 300 ohms. So you clearly want to have a 300, at least 300 ohms. If you have more than 300 ohms, then the current will drop further, and you might see that the LED is not that bright. So you want to just spec it out properly before you use it in a circuit. Okay. So this is a light-emitting diode. We have what is known as a photodiode. Yeah, photodiode, unlike a LED which emits light, a photodiode becomes conducting the moment light falls on it, and so it can be used as a sensor. Okay, so the way a photodiode is connected is as follows. So here we are connecting it in the reverse biased. And then of course you want to put a resistor. Okay, so say you shine light. The moment you shine light, the diode starts conducting. And then you will have a current flowing in the circuit. So do it this way. Positive, so no. no light. The current is 0. And now what we can do is we can shine some light on this. So the light is falling on it. The current in this is greater than 0. Okay, now here's something to note. The current flowing in this diode is the current flowing in reverse bias. It's going to be very little current. This is the reverse bias. So in other words, if you want to use this as a sensor, you want to measure the current, and one way you could measure the current, but another way to measure the current is through measuring the voltage across the resistor. So once you sense that the voltage is non-zero, then you know that current is flowing through the circuit, and that's how you will use this photodiode for as a sensor in your whatever system you build. Okay. Next, let's look at how to analyze circuits involving diodes. Okay. It's actually the thing which makes this slightly non-intuitive or rather hard is that diode is a non-linear circuit. It sometimes conducts, sometimes does not conduct, and that depends on the way a diode is connected. Okay, so this is how you will connect or rather analyze circuits involving circuits with diodes. Okay. So first we'll assume diode is conducting. Okay. Then use KVL, KCL to compute current flow in the diode. Okay. Now we know if it's conducting, then the current direction should be in a particular fashion, right? So it will be this way. This is what happens when it's conducting. But let's say that after doing the analysis number 2, you get that the current flow is in the opposite direction. So if it's in the opposite direction, that it means that your assumption 1 was incorrect. You need to now consider the diode as not conducting and repeat the analysis. Okay. So if current direction is the same as what you assumed, that is diode is conducting, then you are done. So let's call this 3A. If current direction is in the opposite direction, then diode is not conducting. So you should repeat the calculation assuming diode is non-conducting. Okay, so let's see how to apply this on a problem. Okay, here is problem with diodes. Example, 2 volts, positive. This is 2 omega 1 omega 2 omega. Okay, so this is the circuit, and the question is compute the current in each branch. Okay, so this circuit involves a diode, so we want to always start assuming that the diode is conducting. So case 1, assume diode is conducting. Okay, the implications are that the diode is forward biased, and then it also forces us to assume a direction for the current flow. So let's do that first. So let's draw this circuit. And then since it's forward biased, we need to connect it, replace it with a wire. Okay, so let's draw the remaining part of the circuit. Okay, I'm just going to put 1, 2, and 2 and not skip the omegas. Okay, so what I'm going to do is we assume it to be forward bias. So that was here, this is positive, negative, and that means that the current is flowing this way. Let's just assume this to be I1. Okay, and this is our assumption now that it's forward bias, and that implies that the current I1 will flow the way it's shown. The other currents in the circuit are free to assume the way you want. So maybe I could just assume this to be I2. Maybe the current comes like this and splits. You're free to choose the direction of the currents for the other one, but for I1, it needs to be in the direction I've shown. Okay, now let's see what's happening here. So this is positive, and since the current is flowing from here to there, this will be positive potential, negative. Then we would have, this is I2, this will be I2 to I2. Okay, now because this current flows from here to there, this will be positive, this will be negative, same here, positive, negative. And I think now we are all set to analyze this circuit. Okay, so remember that we have 3 unknowns, I1, I2. So we need to generate 3 equations. So my first equation, I'll just get it using KCL. I see that at this node, I goes in, I1 and I2 come out. So we have I minus I1 minus I2 equals 0. Let's do KVL. We have now 3 options. We could do KVL for this branch, this loop, or the big loop. Let's just do it for, let's start doing it for this loop first. Yes, so for that loop, I can do, so there's 2 volts. Remember, this is a positive, negative, and that is in the same direction as this positive, negative. So I can put 2 I's. This should be I. Okay, so 2V, positive, negative, it's connected in the same direction as this one, positive, negative. So this will be 2I. This is positive, negative, so plus 1I1, and that should all be equal to 0. Okay, so note I'm using this polarities to figure out the signs over here. Next, let's look at the full branch. This is the whole branch. Okay, so we do a KVL again. KVL on the big branch. So plus 2, plus negative, so it'll be plus 2I. This is plus negative, so it'll be plus 2I2. This is now connect, the positive is connected to the positive, so this will be minus 2. And then that's it, equals 0. So we can cancel this 2 and this 2. So we are left with 3 equations. I equals I1 plus I2. Rather, let me just write it as this way. I1 plus I2 minus I equals 0. I1 plus 2I equals minus 2. And from the last one, 2I2 plus the 2 and 2 cancel. So I1, I2 plus I equals 0. Okay, so maybe we can just, from third equation, we can solve for I2 is minus I. From the second equation, we can write I1 as minus 2I, and then sub that in the first equation. So we have I1 is minus 2I plus I2, which is minus I, and minus I equals 0. So I comes out to be minus 0. Minus 0.5. That's right. So it's 2 divided by 234. Let me check this again. I2 equals minus I, I1 equals minus 2 minus 2I, which is from the second equation. And then I put that in the first equation. So I1, this is I1. I2 is minus I. So 234, 0.5. Okay, I is minus 0.5, which means that from here, I can compute I1 as minus 2 minus 2I minus 2 minus 0.5, which comes out to be minus 1. Okay, so minus 1, looks like I1 is minus 1. So now we have found that I1 is actually negative of what we originally assumed it to be, which means that the direction of the current is opposite of what we assume, which means that the diode cannot be conducting. It has to be non-conducting. Okay, so since I1 is negative, diode is not conducting. And so we need to repeat this analysis, assuming the diode is not conducting. So now we do case 2, or number 3b, which is plus 2 volts to mega. There is the resistor 1, and then we have open circuit. That's 2 volts to 1. And here I've shown the diode is non-conducting. Okay, now for this circuit, since this is open, there's no current flowing in this branch. The only current will flow would be I, and we can just use KVL. But before that, this is plus minus. The current is flowing from here. It will be plus, this will be minus, it will be plus, it will be minus. And so we can write down now this 2, first 2, this is connected to the positive, so this would be minus 2I, that's positive, and negative, so minus 2I, and this positive has the same sign as this positive. has the same sign as this positive, so it'll be -2 also. This 2 is from here, this 2 is from there. All should be 0, but we see that this 2 cancels with this 2, and so we're left with I equals 0. So the net current in this circuit is 0. So the solution is currents in all branches are 0. So that's the final answer. Okay. Okay, so this is how you would solve a circuit involving diodes. Okay. Okay, I will give you 2 problems for you to solve later on. You might want to read the internet for information and then try to see a reason how this works. So it's something called a flyback diode. Okay, and a flyback diode is used in a circuit to protect a switch from sparking. The way it's connected is as follows. This is an inductor, this is a resistor. And then the diode is connected in this fashion to switch. So VS. L, R. Okay, so a flyback diode is used to protect the switch. Okay. The diode prevents the switch from sparking when it is opened. Okay, so what your goal is to analyze the circuit and how the flyback diode protects the switch. Okay, so do this. Try to reason it out. If you cannot reason it out, you can look at the internet. There are various videos and articles on this. There's another circuit which I would like you to think about. It's not the peak detector. Okay, it's pretty simple circuit involving one diode and a capacitor. Okay, now the purpose of this circuit is to detect the circuit, like the name suggests, is used to detect peak voltage. So what I would like you to do is, I would like you to analyze and so let me give you an input voltage. Your goal is to compute what is the output voltage for that input voltage. So here is a example input voltage, 0, positive, up, down, on. This is your V in, which goes here. Your goal is analyze the circuit and draw V out the function of time. Okay, so that's another question for you to try at home.